Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at one of the processes or the reactions that is involved in organic compounds, and that's the process of hydrogenation. Hydrogenation is one of the processes that can be used to achieve some of the, of course, compounds that we have discussed, especially of the alkane series. And we're going to see that there's a difference between some of the series that we have discussed, especially for aromatic compounds, in that they form a very strong structure that ensures that they are stable. In this case, we're going to see a comparison between benzene and other aliphatic compounds, and we're going to look at one of the processes that is involved, of course, in the reduction process, and that is the pulse reduction. So in this case, I'd like us to just have a keen interest in what we are discussing and try to see the difference between these processes and others that we have discussed or we're going to discuss in our subsequent videos. So without further ado, thank you and welcome. So as I've said, we are going to look at hydrogenation. And hydrogenation, as I've said, is basically the addition of hydrogen. Now that we have looked at the basic structure of some of the organic molecules, there are some of the organic molecules that can undergo change in order to form other products or a transformation from one organic series to another. For instance, we can transform alkenes to alkanes through the addition of hydrogen. So in this process, this is basically the simple definition of a process that we can call hydrogenation. That is transformation of one organic or a series of organic compounds from one form to another. So in this case, hydrogenation of benzene is a process that is achieved under high pressure of hydrogen in the presence of a catalyst. And of course, we can give an example of that. That's the platinum catalyst. As we have said, under high pressure. And then this, of course, is going to give us a basis for our discussion for today. Now, as I've said, I've talked about the condition of a high pressure. So I'm going to give a small demonstration to show the difference between the reaction or the hydrogenation of an aliphatic compound and benzene. And that is going to give us a clue or a basis by which we are going to determine the stability of that benzene molecule as compared to other aliphatic compounds. So I've drawn two illustrations on the board for illustration purposes. That's a transformation from a double bond series, that's an alkene to alkane, and this process entails the addition of hydrogen. The two processes, I can call this one process 1, or just reaction 1 and reaction 2. So both of them entail the addition of hydrogen, therefore they are hydrogenation processes, and there is addition of hydrogen to the first molecules in order to form the product. So in this case, the difference between the two is that the first one entails or involves 1 atmosphere, while the other one involves 150 atmospheres. That's a very big difference. But of course, the temperatures we can see on the catalyst, the conditions are the same, only that it occurs under very high pressure. So the transformation from an alkene to alkane, or from a benzene to a cyclohexane, involves a very high temperature, and this one basically confirms the stability of aromatic compounds, in that such a compounds like benzene are stabilized by the localization of electron densities around the carbons, of course, as we have said, around the carbons of the aromatic structure. So basically this process, as I've said, is very essential. Now that the products that are formed, like the one that we are seeing here, this is cyclohexane. These products are very useful, especially for that one is used as an organic solvent, or maybe a precursor in the production of other. As I've said, this basically is one of the ways in which we can achieve alkanes from alkenes, and a similar structure or compound. So these are some of the conditions, but in this our demonstration is actually to illustrate that the concept of high pressure confirms that the aromatic series are stable as compared to the aliphatic ones. So we're going to look at a second process, or maybe a topic that we were also to discuss for today. That's the batch reduction process, and also we're going to see on how this can be achieved and some of the conditions which are necessary for this. So for hydrogenation processes, this is one of the ways in which it can be achieved. The batch process reduction process also involves the addition of course, the reduction of the double bonds, and we're going to see on how this process occurs using a reaction mechanism. Now, the batch reduction is a reduction process that, as we can see from this, when this product is subjected to these conditions, when this molecule is subjected to these conditions, that is sodium in liquid ammonia, and this under this range of temperatures we are able to achieve a product. Of course, that is a cyclohexene, which is a transformation from alkane. So in this case, it shows that there is addition, as we know that the formula for benzene is C6H6, but there's addition of extra hydrogens on the second molecule, in the sense that we're going to have this is another one. At those specific points. So if so this one is just H. So if you try to look at the number of hydrogens that have been added at that particular point, so we can give the formula for this as C6H. This is 1, 2, 3, 4, 5, 6, 7, H8. So this is a cyclo. This is a cyclo compound, of course, which is cyclohexadiene. Which has been formed from the benzene, as we can see when it is subjected to these conditions. This is one of the reduction processes that we are talking about through the addition of hydrogen. Now we're going to look at the reaction mechanism for this in order for us to understand how the concept works and try to see whether there are other conditions that it can be involved. Of course, there is in addition, this works in the presence of alcohol, and we're going to see now mechanism on how the role of alcohol plays an important role in achieving that product. Now, the reaction mechanism for the batch process that we have mentioned in, of course, the last illustration that we have given happens in the conditions of high pressure. So I've illustrated when I had given two illustrations for the aliphatic or the alkene and the cyclo, that is the benzene. And the comparison of 1 atmosphere to 150 shows the stability of benzene. So in this case, I'm going to illustrate the reaction mechanism that leads to the formation of a cyclohexadiene, which of course is going to be a product there. And in this case, of course, we're going to see that the sodium that is, of course, in liquid ammonia acts as an agent that adds electrons to form anions. So we are going to have this sodium at this particular point, and then the sodium is going to add electrons at this point, and then we are going to have this bond. These are half arrows. We shall talk about the concept of arrow pushing when we are talking about reaction mechanisms, especially in organic synthesis. So the first process here is the formation of a radical anion by addition of solvated electrons to the aromatic ring, as I have illustrated. So the concept of solvated electrons in this case means that free electrons, which are in a solution, of course, and that can behave as an ion. So when that process occurs, of course, there is a formation of as I've said, the the products that I've illustrated. So we shall have these electrons at those particular point. Of course, I've mentioned about the formation of a radical, an ion, by the addition of those electrons to the aromatic ring. So in this case, the second process, there's going to be an arrangement for this. We shall have this one move here, and then this one, of course, because of this hydrogen, I'm just going to use this, although it's supposed to be the other way around. So that is to illustrate how this charge is formed at this particular point, and there's going to be that one at that point. So we shall have this intermediate product that has been illustrated. So as we have said, alcohol forms the source of protons, and we shall have just a general representation for an alcohol as such. So in this case, this negative charge is going to pick on that proton from that point, and it will form this intermediate product that I've drawn. So we shall have still that product as such, and then there will be a negative charge at that point. And then the subsequent there will be continuation of addition of course the proton that I've illustrated, which of course as we have said, the alcohol supplies the protons to the radical anion in a subsequent intermediate product to a last carbanion that we have illustrated. So this one will just a minute. So in this case, there will be that process whereby that proton will be picked in order to form the last product, which is of course a cyclohexadiene. It's an intermediate I'm trying to confirm. For that case, there will be a formation, of course, of an alkoxide, which is generally represented as such. So this reaction mechanism is the one that is involved in the batch process, and this leads to the formation of a cyclohexadiene that we have illustrated below. Now, apart from others, this is one of the processes in which we can be able to achieve a reduced product from the benzene ring that we have mentioned. Now, this process is very essential because the process is selective in nature, and especially in the processes which are used in reducing the double bonds. So we can be able to use this process when we are trying to synthesize or targeting a specific double bonds in the formation of other organic molecules or products from molecules such as benzene. So in this case, of course, we are going to mention other additional information in case we come across the processes or other reactions which require a mention of a batch reduction or hydrogenation. So for that case, we shall stop there for today. Thank you. Bye. God bless you.